The night of December 26, 1942, North Atlantic, approximately 60 miles northwest of Rockall. Commander Donald Macintyre stood on the bridge of HMS Hesperus, watching his radar operator's face illuminated by the faint green glow of the Type 271 display. The sea was black, no moon, no stars. Just endless darkness broken occasionally by spray caught in the destroyer's running lights. Down in the radar office, directly beneath the bridge, leading Seaman Thomas Richardson stared at the cathode ray tube, watching the sweep line paint across the screen with each rotation of the cheese antenna mounted above his head. He had been at this station for 6 hours, and his eyes burned from the strain of watching for the telltale blip that would indicate a surfaced submarine. Then he saw it. A contact, bearing 315 degrees. Range 4,000 yards. Richardson's hand moved to the voice pipe without conscious thought. Radar to bridge. Contact bearing 315, range 4,000 yards. Small, possibly U-boat. Macintyre felt his pulse quicken but kept his voice level. Helm, come left to 315. All ahead full. Action stations. The alarm bells rang through Hesperus, bringing her crew to battle stations with practiced efficiency. In the darkness ahead, invisible to every man aboard except through the electronic eye of their radar, U-357 was running on the surface, recharging batteries after a long submerged patrol. Her commander, Captain Lieutenant Adolf Kellner, had no idea he had been detected. His Matox radar detector sat silent. The British destroyer, approaching at 30 knots, was using frequencies the German warning receiver could not detect. What Kellner could not know, what no German naval commander yet understood, was that the rules of nighttime submarine warfare had changed forever. For 2 years, U-boats had owned the darkness. They could surface at night with near impunity, attacking convoys, while escorts groped blindly through the gloom. Visual lookouts were useless in these conditions. Sound detection worked only when submarines were underwater. The night had been Germany's ally, protecting Donitz's boats as reliably as armor plate. But 6 months earlier, in the spring of 1942, that advantage had begun to evaporate. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The transformation had started not with a single invention, but with a critical mass of British desperation, American manufacturing capacity, and one specific piece of copper that changed naval warfare forever. September 1940. A black metal box arrived in America, carried by British scientists who understood they were delivering their nation's most closely guarded secrets to a country still officially neutral. Inside that box, wrapped in protective material, sat a cavity magnetron. A device so revolutionary that Winston Churchill himself had agonized over deploying it operationally, fearing exactly what would eventually happen, that it would be captured, that the Germans would copy it, that Britain's technological advantage would evaporate. The magnetron was elegant in its simplicity. A copper cylinder, roughly 8 centimeters in diameter, with precision-machined cavities arranged around a central cathode. When powered, it generated microwave radiation at frequencies far higher than anything previously practical for military equipment. This meant radar beams that were narrower, more focused, and capable of detecting smaller objects at greater range than the meter wavelength systems currently in use. More critically, it operated at frequencies German radar detectors could not sense. The technical specifications were staggering to American scientists who examined it. The British magnetron produced 1,000 watts of microwave power at 10 centimeter wavelength. American experimental systems at that time could barely generate 10 watts. This was not an incremental improvement. This was a leap of an entire generation in radar technology. The Americans had been working on radar for years, but they had hit fundamental barriers in power generation at high frequencies. The vacuum tube technology available simply could not generate sufficient microwave power for military applications. British scientists, facing annihilation from German bombing campaigns and U-boat strangulation of their supply lines, had somehow solved problems that American engineering declared unsolvable. The TISAD mission's arrival triggered an explosion of American radar development. The Massachusetts Institute of Technology established the Radiation Laboratory specifically to exploit magnetron technology. Within months, prototype radar systems using the British magnetron were under development for aircraft, ships, and ground installations. But creating a revolutionary device in a laboratory and deploying it effectively in combat are entirely different challenges. The story that matters is not about the scientists who invented the magnetron. It is about the operators who learned to use it, the commanders who trusted it, and the incremental discoveries made by men at sea who transformed an experimental technology into a war-winning weapon. By early 1941, the Royal Navy had developed the Type 271 radar specifically for escort vessels. It used the cavity magnetron to generate 10-centimeter wavelength pulses, reflected off surfaces, and displayed on a cathode ray tube. The antenna was small enough to mount on corvettes and frigates, the ships that formed the backbone of convoy escorts. The resolution was high enough to detect a surfaced U-boat at approximately 3 miles range, and theoretically could detect just a periscope at 900 yards. Theoretically, the prototype Type 271X was fitted to HMS Orchis in March 1941 and declared operational in May. By October, approximately 30 sets were in operation across the fleet. The technology worked. Ships equipped with Type 271 could detect submarines in conditions where visual observation was impossible, but early operational experience revealed something the laboratory tests had not. Having the technology was not the same as knowing how to use it effectively. The radar operators, hastily trained on equipment so new that proper doctrine did not yet exist, faced a steep learning curve. The cathode ray display showed contacts, yes, but distinguishing a U-boat from a whale, from a patch of rough water, from the wake of a friendly ship required experience that could only be gained through hours of staring at the green screen. The antenna had to be manually rotated using a steering wheel connected to a shaft passing through the bridge roof. Operators quickly learned that smooth, steady rotation produced better results than quick sweeps. They discovered that contacts appeared and disappeared based on sea state, that the radar beam reflected differently off submarines depending on their angle to the destroyer, that metal structures on friendly ships could create false echoes that looked exactly like enemy contacts. None of this was in the manuals, because the manuals were still being written. Each ship with Type 271 was conducting an operational experiment, learning through trial and error how to transform electromagnetic returns into actionable intelligence. Lieutenant Commander A.A. Tite commanded HMS Hesperus when she received her Type 271 installation in early 1942. The destroyer had been laid up for repairs in Falmouth after ramming U-93 in January, an engagement that had bent her bow plating and damaged her forward hull. While shipwrights repaired the structural damage, technicians installed the new radar system. The distinctive Perspex lantern housing the cheese antennas was mounted directly on the bridge roof. Coaxial cables, thick as a man's thumb, ran down through the bridge structure to the radar office where the receiver and display were located. Tite watched the installation with interest but skepticism. He had commanded destroyers for years. He understood sound detection, visual search patterns, the tactical geometry of convoy escort. This radar device represented something entirely new, a way of seeing that contradicted everything his experience had taught him about naval warfare. You could not see through darkness or fog, except now, apparently, you could. The initial sea trials were promising. Steaming out of Falmouth in early March 1942, Hesperus detected a British submarine conducting training exercises at ranges that would have been impossible with visual observation alone. The radar worked, but using it in actual combat against a U-boat commander who would take evasive action the moment he suspected detection would be entirely different from tracking a cooperative training target. In June 1942, Commander Donald Macintyre returned to Hesperus, resuming command of the ship he had originally commissioned in January 1940. Macintyre had been away commanding HMS Walker and the 5th Escort Group, achieving considerable success, including sinking the U-boats commanded by two of Germany's most famous aces, Otto Kretschmer and Joachim Schepke. He was exactly the kind of aggressive, tactically innovative commander the Royal Navy needed for testing new equipment in combat conditions. Macintyre understood immediately that Type 271 represented a fundamental shift in anti-submarine warfare. For the first time, escorts could detect surfaced U-boats at night beyond visual range. This meant U-boats could no longer safely run on the surface to recharge batteries or make high-speed transits. It meant night attacks on convoys, previously almost impossible to defend against, could now be intercepted. But it also required completely rethinking how escorts operated. Traditional anti-submarine tactics assumed you detected the U-boat visually or through sound. With radar, you had advance warning, but only if your operators could correctly interpret what the display was showing them. Macintyre spent considerable time in the radar office, watching his operators work, learning to distinguish meaningful contacts from the clutter that filled the screen. He discovered that experienced operators developed an almost intuitive sense of what contacts mattered. They could see patterns in the noise that inexperienced operators missed. They understood that a contact which appeared briefly, then disappeared, then reappeared slightly off the original, bearing was probably a submarine running at periscope depth, with just the conning tower breaking the surface. They learned that the reflected signal from a surfaced U-boat had a specific quality, a particular sharpness on the screen that differed from returns off waves or debris. This knowledge was not written down anywhere. It existed only in the collective experience of the men who operated the equipment night after night, convoy after convoy. The autumn of 1942 brought continuous gales around Iceland. Hesperus and her escort Group B, too, spent months battling weather so severe that green water swept the decks, even in a destroyer displacing 1,400 tons. The radar operators worked in conditions that would have been considered impossible in peacetime. The ship rolled 30 degrees to either side. Electronic equipment, barely proven in laboratory conditions, was expected to function reliably while being subjected to shock loads that would destroy civilian electronics. And it worked. Not perfectly, not consistently, but well enough that commanders began to trust it. In October, while escorting convoy ONS 138, Hesperus used her Type 271 to maintain contact with 2 U-boats for 2 full days, keeping them submerged and unable to attack the convoy. The U-boats escaped, but the convoy passed through safely. That was a victory by the new mathematics of anti-submarine warfare. Every convoy that reached port intact meant tonnage that stayed in service, cargoes that reached British ports, supply lines that remained open. The U-boats did not need to be sunk to be defeated. They only needed to be prevented from sinking merchant ships faster than Allied shipyards could replace them. By December 1942, Hesperus had been operating with Type 271 for 9 months. Her radar operators had hundreds of hours of experience. They had learned to compensate for side echoes caused by the lantern's support pillars, adjusting their interpretation of what the display showed. They had developed techniques for tracking contacts through heavy seas when the radar return faded in and out. They had learned, through experience that cost merchant sailors their lives when mistakes were made, to distinguish U-boats from whales, from friendly ships, from patches of disturbed water. This accumulated knowledge, this operational art developed through trial and error, was what would matter on the night of December 26th, when Hesperus encountered U-357 in total darkness. Convoy HX-219 had departed Halifax on December 16th, bound for Liverpool with 44 merchant ships carrying war materials from North America. The escort group included Hesperus as senior ship, the destroyer HMS Vanessa, and several corvettes. The crossing had been difficult. Winter storms in the North Atlantic produced seas that damaged ships and exhausted crews. By December 26th, the convoy was approaching the most dangerous phase of the crossing, entering the area where German U-boat patrol lines waited to intercept eastbound convoys. U-357, a Type 7 sea submarine commanded by Kapitänleutnant Adolf Kellner, was part of a patrol line searching for convoys northwest of Ireland. The boat had been at sea for several weeks, operating in conditions that tested even experienced crews. Being locked inside a steel tube, breathing recycled air heavy with diesel fumes, sleeping in shifts in bunks that never dried out, eating food that tasted of mold and fuel oil, watching condensation drip from every surface. This was the reality of U-boat operations in the North Atlantic winter. But at night, you could surface. You could run the diesel engines, recharging the batteries that powered the electric motors used underwater. You could open the hatches, letting fresh air flush through the compartments. You could make 15 knots on the surface compared to 7 submerged, allowing you to intercept convoys or transit to patrol areas. The darkness had always been safe. British escorts with their sound detection were nearly blind at night. Visual lookouts could not see a low-profile submarine even at close range in these conditions. December 26, 1942, approximately 2100 hours. U-357 surfaced after spending the day submerged, running on battery power to avoid aircraft detection. Kellner ordered the diesel engines started, beginning the battery charging cycle that would take several hours. The U-boat's lookouts scanned the horizon, seeing nothing but darkness and the white caps of breaking waves. The Metox radar detector was operating, its distinctive crossed wooden antenna mounted on the conning tower. It remained silent. No British radar emissions detected. As far as Kellner and his crew knew, they were alone in the vastness of the Atlantic, invisible in the darkness. They were wrong. 60 miles to the east, Hesperus was steaming on the port wing of convoy HX-219. Below the bridge, leading Seaman Richardson sat at his Type 271 display, conducting the methodical sweep he had performed thousands of times before. Rotate the antenna through its arc. Watch the screen. Distinguish meaningful contacts from background noise. His eyes were adapted to the dim green glow, able to pick out the faint returns from merchant ships in the convoy several miles ahead. Then, at the edge of his screen, a new contact appeared. Small, distinct, bearing 315 degrees, range 4,000 yards. Richardson's training took over. He measured the contact's characteristics. Size of return suggested something small. Shape of the echo had that particular quality he had learned to associate with submarines. Movement was steady, no erratic course changes that would suggest a whale or debris. Range was opening slightly, indicating the contact was moving away. Radar to bridge, contact bearing 315, range 4,000 yards. Assessed as possible submarine. Macintyre's response came immediately. Action stations, come left to 315. All ahead, full. Hesperus turned toward the contact, her turbines accelerating to full power. Within minutes, she was making 30 knots, closing on the radar return that represented U-357. On Hesperus's bridge, Macintyre made rapid calculations. If the contact was a U-boat, and if it was running on the surface, he had perhaps 10 minutes before the submarine detected his approach and crash-dived. Once submerged, the U-boat would be much harder to find, detected only by sound, which was unreliable in these sea conditions. The key was to close the range before the submarine realized it was being hunted. This was where Type 271's invisible nature mattered. The German Metox detector could not sense the 10-centimeter radar pulses. U-357's crew had no idea a British destroyer was racing toward them at 30 knots. At 3,000 yards range, Macintyre made his decision. Illuminate target. The searchlight mounted on Hesperus's bridge suddenly blazed to life, its beam lancing across the dark water toward the bearing, indicated by radar. For a frozen moment, nothing. Then the light caught a shape. A submarine surfaced, caught completely by surprise. On U-357's bridge, the sudden glare of the searchlight triggered instant chaos. Kellner screamed orders. "Alarm! Dive! Dive! Dive!" The klaxon shrieked through the boat. Men tumbled down the conning tower hatch. The diesel engines cut off, electric motors engaged. Vents opened, allowing seawater to flood the ballast tanks. But it was too late. Hesperus was only 1,500 yards away, closing at 30 knots. Macintyre could see the U-boat's deck already awash as she began to submerge. "Hard right rudder, Prepare to ram. The destroyer's bow swung toward the diving submarine. Aboard U-357, Kellner knew they would not make it. The British destroyer was too close, moving too fast. The boat was only partially submerged, vulnerable and unable to maneuver. Then Hesperus struck. The impact was devastating. Hesperus's reinforced bow hit U-357 just aft of the conning tower, with the full momentum of 1,400 tons moving at 30 knots. The collision flung Kellner and the lookouts from the bridge into the sea. Below, in U-357's pressure hull, the impact buckled frames and ruptured seams. Seawater poured through the damaged sections. The boat was doomed. Macintyre ordered Hesperus's engines reversed, pulling clear of the sinking submarine. Depth charges were set for shallow detonation and rolled off the stern, ensuring the U-boat could not recover. Within minutes, U-357 slipped beneath the surface for the last time. Her crew of 47 men drowned in the frigid Atlantic. Only 6 survivors were pulled from the water, including Kellner himself, hypothermic but alive. Aboard Hesperus, damage control parties assessed the collision's effects. The bow was buckled, the forward hull plates were bent. Water was entering the damaged sections, though not fast enough to threaten the ship. She could make port under her own power, but she would need extensive repairs. Macintyre dictated his after-action report, documenting the engagement that had just ended. His report was factual, almost clinical. Radar contact at 4,000 yards, illumination at 3,000 yards, successful ramming of surfaced U-boat, enemy vessel destroyed. What the report could not convey was the significance of what had just occurred. A British destroyer had detected a German U-boat in total darkness, closed to ramming range before the submarine could dive, and destroyed it using technology the Germans could not detect. This was the new reality of Atlantic warfare. The night no longer protected U-boats. The darkness that had been Germany's ally for 2 years had become a liability. German submariners who had grown accustomed to surfacing safely at night now faced the terrifying possibility of sudden attack from enemies they could not see or detect. The psychological impact would prove as important as the tactical advantage. When Hesperus limped into Liverpool on December 28 for repairs, her bow crumpled from the collision. She carried physical evidence of how naval warfare had changed. The damage was severe enough to require 3 months of repair work. While shipwrights straightened frames and replaced hull plating, Macintyre's report worked its way through Royal Navy channels, being read by officers who understood exactly what Type 271 had just accomplished. The ramming of U-357 was not the first successful radar-assisted U-boat kill. HMS Hesperus herself had sunk U-93 using radar in January 1942. HMS Orchis, the first ship equipped with Type 271, had contributed to the sinking of U-433 in November 1941, the first U-boat destroyed with assistance from centimetric radar. But the December engagement was significant because of how completely the technology had matured in just 20 months since deployment. From experimental equipment that operators barely understood, Type 271 had evolved into a weapon system that escort commanders trusted enough to conduct high-speed attacks in total darkness against targets they could not see. The learning curve had been steep, paid for in merchant ships sunk while operators learned to distinguish U-boats from whales. But by winter 1942, that learning was complete. The operational techniques developed through hundreds of convoy escorts were now doctrine, taught to new operators joining the fleet. Richardson, the radar operator who had detected U-357, would later train other operators, passing on the accumulated knowledge of what contacts looked like, how to distinguish meaningful returns from clutter, when to trust the radar, and when to remain skeptical. This knowledge transfer, from experienced operators to novices, was crucial to scaling the technology across the fleet. By May 1942, 236 Royal Navy ships carried centimetric radar. By the end of 1943, virtually every escort vessel in the Atlantic had Type 271 or its successors installed. The Germans would eventually develop countermeasures. The Naxos radar detector, introduced in September 1943, could detect centimetric radar, though its warning range was too short to provide adequate time to dive. By then, the Allies were already deploying 3-centimeter radar systems that Naxos could not detect. The technological race continued, but the fundamental advantage had shifted permanently. The Germans never solved the mass production problem for cavity magnetrons. They could build experimental units, but they lacked the industrial capacity and critical materials to deploy the technology at scale. British and American factories produced tens of thousands of magnetrons. German production measured in the hundreds. This disparity in manufacturing capacity meant that Allied radar superiority only increased as the war progressed. The story of Type 271 is often told as a tale of British scientific ingenuity or American industrial might. Those narratives are true but incomplete. The real story is about the men who learned to use the equipment. The radar operators who spent thousands of hours staring at cathode ray displays, developing the ability to see patterns in electronic noise. The commanders who trusted the technology enough to conduct night attacks at high speed against targets they could not visually confirm. The technicians who kept the equipment functioning in conditions that would destroy civilian electronics. These were not officially recognized innovations. There were no patents filed for the techniques operators developed to distinguish U-boats from false contacts. There were no academic papers published about the optimal method for tracking a submarine through heavy seas when the radar return faded intermittently. This knowledge existed only as operational art, passed from experienced personnel to novices through demonstration and practice. Yet this unofficial, undocumented learning process was what transformed an experimental technology into a war-winning weapon. By early 1943, Type 271 and its successors had fundamentally altered the Battle of the Atlantic. By early 1943, Type 271 and its successors had fundamentally altered the Battle of the Atlantic. The statistical evidence was undeniable. In the 6 months before widespread deployment of centimetric radar, from July through December 1942, German U-boats sank approximately 450 merchant ships in the Atlantic. In the 6 months following deployment, from January through June 1943, sinkings dropped to approximately 300 ships, despite more U-boats being at sea. The exchange rate was collapsing. For every merchant ship sunk, the Allies were destroying more U-boats. The mathematics that Grand Admiral Karl Dönitz relied upon, the calculation that U-boats could sink Allied shipping faster than it could be replaced, was breaking down. The turning point came in May 1943, a month that would become known among U-boat crews as Black May. Throughout that month, Allied escorts equipped with centimetric radar, working in coordination with aircraft carrying the same technology, savaged the U-boat force with unprecedented effectiveness. The convoy battle for ONS-5 in late April and early May marked the shift. 30 U-boats attacked a slow convoy of 43 merchant ships. The Germans managed to sink 12 merchants but lost 7 U-boats with another 5 severely damaged. For the first time in a major convoy battle, the U-boats suffered losses approaching their successes. The exchange ratio had become unsustainable. 2 weeks later, convoy SC-130 demonstrated complete Allied dominance. 37 merchant ships in convoy, 0 lost despite attacks by 25 U-boats from 3 patrol lines. The German forces lost 3 U-boats. Throughout May, the losses mounted relentlessly. By month's end, 41 U-boats had been destroyed, representing approximately 25% of operational strength. This was catastrophic. The U-boat force could not sustain such losses. Experienced commanders were dying faster than training schools could replace them. New boats were being sunk on their first patrols before crews learned combat survival techniques. On May 24, 1943, Dönitz made the most painful decision of his career. He ordered all U-boats to withdraw from the North Atlantic temporarily, conceding that Allied technological superiority had made operations unsustainable. The immediate statistical impact was dramatic. In June 1943, only 17 merchant ships were sunk in the Atlantic. In July, only 9. The Allied supply line, which had seemed on the verge of being severed in March, became secure. The vast convoys that would support D-Day and the liberation of Europe began assembling in American ports, protected by technology that had rendered Germany's most effective weapon obsolete. But the human cost on both sides remained staggering. Of the approximately 40,000 men who served in U-boats during the war, approximately 30,000 would die, representing a 75% casualty rate, the highest of any military service on either side. They drowned in steel cylinders crushed by depth charges. They suffocated when air systems failed under prolonged attack. They burned when diesel fuel ignited from combat damage. They died knowing their equipment was inferior, their missions increasingly futile, their sacrifice changing nothing in the war's strategic outcome. The interrogation reports from captured U-boat crews during summer and fall of 1943 revealed the profound psychological impact of technological inferiority. Allied intelligence officers, initially confused by the defeatism among prisoners who had been fanatical believers in German victory just months earlier, gradually recognized they were witnessing a unique phenomenon. These men had not been defeated in conventional battle. They had been rendered obsolete by science, hunted by technology they could neither see nor counter. Korvettenkapitän Werner Henke, commanding U-515, was captured in April 1944 after his boat was sunk by American escort carriers. During interrogation at Fort Hunt, Virginia, he provided testimony that revealed the profound demoralization caused by the Allied radar advantage. "We knew by mid-1943 that the war was lost," Henke told his interrogators during sessions conducted between May and June 1944. Not because German soldiers lacked courage or skill, but because Allied technology was systematically destroying every advantage we once possessed. The Metox detector became useless against the new radar. We called it the grave bell among crews because when it failed to warn of approaching aircraft, it rang only for our funerals. Later models that could detect centimetric radar arrived too late for most boats. Even when it worked, we could only detect emissions at short range, while Allied aircraft detected us from beyond visual distance. We could dive when warned, but aircraft would circle overhead, calling destroyers to depth charge us. We could not escape what we could not see until it was too late. Oberleutnant Zur C. Herbert Werner survived the war after serving on 5 different U-boats, including surviving the sinking of U-612 in August 1942 and U-415 in July 1944. His post-war memoir, Iron Coffins, published in 1969, became one of the most widely read accounts of the U-boat war from the German perspective. Werner described the psychological impact of fighting against superior Allied technology. Every patrol after May 1943 was a survival exercise disguised as a military operation. We understood that Allied radar could detect our periscope wake, our snorkel exhaust, even our conning tower awash. We travelled submerged far longer than boats were designed to endure, breathing foul air, conserving battery power, surfacing only when fuel and oxygen forced us. The Atlantic, which we had dominated in 1942, became an enemy more dangerous than British destroyers. It hid Allied aircraft above fog and Allied ships beyond horizons, while revealing our every movement to enemies equipped with technology that gave them complete tactical advantage. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical investigations continued through 1943 and 1944, as German engineers desperately attempted to develop countermeasures. They produced the LMS-10 Magnetron, a direct copy of the British CV-64 design. However, production was severely constrained by material shortages, particularly the cobalt required for permanent magnets. Most early units required magnets salvaged from captured British aircraft, making large-scale production impossible. Telefunken began developing an indigenous German magnetron designated LMS-12, attempting to adapt the British design to materials available in Germany. But this development would not reach even limited production until April 1944, far too late to affect the war's outcome. Actual production of German cavity magnetrons totaled several hundred units across all variants by war's end. This contrasted starkly with Allied production, which numbered in the tens of thousands. Radar warning receivers that could detect centimetric frequencies were developed in parallel efforts. The Naxos system, designated FUG 350 Naxos Z for aircraft and FU MB7 Naxos U for U-boats, was introduced in September 1943. The system could theoretically warn U-boats of approaching aircraft equipped with ASV Mark III radar operating at 9.1 cm wavelength. However, by the time Naxos entered operational service, Allied scientists had already developed 3 cm radar systems against which Naxos was blind. The Germans were perpetually one generation behind, forever attempting to counter yesterday's threats, while new systems rendered their countermeasures obsolete before they could be widely deployed. The German Navy also attempted tactical adaptations to cope with Allied radar superiority. U-boats were fitted with additional anti-aircraft guns, with some boats designated as flak boats carrying quad 20mm mounts and heavy AA armament. The theory was that if boats could not hide from radar-equipped aircraft, they should remain surfaced and fight it out with anti-aircraft fire. This proved disastrous in practice. Allied aircraft could detect U-boats from ranges far exceeding effective anti-aircraft fire. The aircraft's speed advantage meant it could choose when and how to attack, while the stationary boat simply waited to be attacked. The flak boat program cost more submarines than it destroyed aircraft, representing another failed attempt to counter Allied technological advantage through tactics alone. New submarine designs incorporating snorkel systems represented another attempt to adapt to Allied technological superiority. The snorkel, originally a Dutch invention from 1938 captured when Germany overran the Netherlands in 1940, was initially ignored. German engineers began testing snorkel systems in summer 1943, with operational use beginning in early 1944. The snorkel allowed boats to run diesel engines while submerged at periscope depth, recharging batteries and transiting without surfacing. This reduced vulnerability to radar-equipped aircraft. However, snorkels were far from perfect solutions. They left a wake visible to radar, particularly in calm seas. They limited speed to a few knots. They required excellent seamanship in rough weather, as waves washing over the snorkel head would trigger automatic valves that momentarily cut air supply, creating uncomfortable and dangerous pressure fluctuations inside the boat. By mid-1944, approximately 50% of U-boats operating from French bases were equipped with snorkels. While this improved survival rates somewhat, it could not reverse the fundamental strategic defeat. U-boats equipped with snorkels could evade some attacks, but they could not sink enough merchant ships to affect Allied logistics. The Battle of the Atlantic had already been decisively lost. The revolutionary Type XXI Electra boat represented Germany's most ambitious attempt to regain technological parity. This radical design featured streamlined hull form, triple battery capacity, 17.2 knots submerged speed compared to 7.6 knots for conventional Type 7 boats, 6 bow torpedo tubes with hydraulic reload capability, allowing 18 torpedoes to be fired in under 20 minutes, and sophisticated sonar systems. The Type XXI could theoretically outrun most surface escorts while submerged and remain underwater for extended periods. Had this design entered service in 1943 rather than 1945, it might have significantly extended the Battle of the Atlantic. However, rushed production created severe quality problems. Of 118 boats constructed, only 4 were fully combat-ready before war's end. Only 2 conducted combat patrols in April and May 1945, achieving no sinkings before Germany's surrender. The final U-boat patrol of the war demonstrated both the potential and the futility of German technological efforts. U-2-511, the first Type XXI Electra boat to see operational service, departed on April 30, 1945, commanded by Korvettenkapitän Adalbert Schnee, one of Germany's most experienced and successful U-boat commanders. On May 4, 1945, U-2511 detected a British cruiser task force and executed a perfect attack approach, reaching firing position undetected despite Allied radar coverage. The boat's superior underwater speed and silent running capabilities allowed it to close to attack range without detection. Schnee did not fire. Germany had already announced surrender negotiations. He surfaced and radioed his position on May 5, 1945, ending the U-boat war not with violence but with acceptance of defeat. In his post-war memoir, Schnee reflected on the bitter irony. "We proved that day what the Type 6I could have achieved had it entered service a year earlier, but such demonstrations were meaningless. The Allies had already won through industrial capacity and technological innovation deployed in 1942 and 1943. Our most advanced technology arrived when the war was already lost." The statistical summary of the Battle of the Atlantic confirms the decisive impact of the cavity magnetron's introduction in early 1943. From January through May 1943, during the period when first-generation ASV Mark III radar was being deployed but before full operational coverage was achieved, U-boats sank 245 merchant ships, totaling approximately 1,289,000 tons. German losses during this period were 95 U-boats, including the catastrophic 41 boats lost in May alone. From June 1943 through May 1944, after centimetric radar equipped most Allied aircraft and ships operating in the Atlantic, merchant ship losses dropped to 185 ships, totaling approximately 819,000 tons, despite more U-boats being at sea. German losses during this period climbed to 237 U-boats. The exchange rate had reversed completely. In March 1943, at the peak of U-boat effectiveness, Germany sank 82 merchant ships, totaling 476,000 tons in the Atlantic, 120 ships worldwide, totaling 693,000 tons, while losing 12 U-boats. By summer 1943, after centimetric radar deployment became widespread, typical months saw fewer than 20 merchant ships sunk while U-boat losses remained in double digits. The tonnage war had become unwinnable. The post-war examination of captured U-boats by Allied technical teams revealed desperate German attempts to adapt to Allied radar dominance through improvised countermeasures. Some boats had been covered with experimental radar-absorbent materials, crude attempts at stealth that added weight, reduced performance, and provided negligible reduction in radar returns. The materials available to Germany in 1943 and 1944 were inadequate for effective radar absorption at centimetric wavelengths. Others carried inflatable decoy balloons designed to create false radar targets, devices that sometimes worked but could not be deployed when submerged or in heavy seas, limiting their tactical utility. Still others had been fitted with modified exhaust systems designed to minimize the radar signature of snorkel emissions, modifications that reduced diesel efficiency without eliminating radar detection. Each adaptation represented German engineering ingenuity applied to an essentially unsolvable problem. You cannot hide from electromagnetic radiation using mechanical solutions alone. The physics were unforgiving. Allied radar operated at wavelengths and power levels that made submarines visible regardless of weather, darkness, or evasive maneuvers. Only remaining completely submerged offered any protection. But battery technology in 1943 and 1944 could not support the extended underwater operations that would have been required to avoid detection entirely. German submarines were trapped by the limitations of their own technology. They were visible to enemies they could not see, hunted by weapons they could not effectively counter, and forced to operate in an electromagnetic environment where the Allies possessed complete dominance. But perhaps the most important lesson from this story transcends radar and submarines. The transformation of Type 271 from experimental equipment to war-winning weapon was not primarily about the technology itself. It was about the people who learned to use it. Commander Donald Macintyre returned to sea in March 1943 after Hesperus completed her repairs from ramming U-357. On April 23, while escorting convoy ONS-4, Hesperus sank U-191 using the newly installed Hedgehog anti-submarine mortar, guided to the target by Type 271 radar. Less than 3 weeks later, on May 12, she sank U-186 while defending convoy SC-129. Both kills demonstrated how completely the technology had matured. Radar detected the submarines, Hedgehog destroyed them, all without the escort ever losing contact or giving the U-boats opportunity to escape. Macintyre would go on to command other ships and other escort groups, continuing his successful anti-submarine career until war's end. He retired from the Royal Navy in 1955 after a 33-year career and became an author, writing numerous books on naval history, including his memoir U-Boat Killer, published in 1956. He died in May 1981 at age 77, having lived to see the technology he helped develop become the foundation for modern naval warfare. HMS Hesperus survived the war, escorting the ships carrying the Norwegian government in exile back to Norway in May 1945. She was eventually converted to a target ship and broken up in 1946, her hull worn out from 5 years of continuous Atlantic service. But her legacy lived on in every escort vessel equipped with radar, in every U-boat kill made possible by technology the Germans could not detect. The radar operators who learned to interpret the green glow of cathode ray displays, distinguishing U-boats from whales through experience rather than formal training, were never officially recognized for their contribution. There were no medals for developing the technique of tracking contacts through heavy seas. There were no commendations for learning to identify the specific quality of radar returns that indicated a submarine rather than surface debris. This knowledge was simply absorbed into operational doctrine, taught to new operators as standard procedure, its origins in improvisation and trial and error forgotten. Yet this unofficial innovation, this learning process, conducted by men at sea rather than scientists in laboratories, was what made the technology actually work in combat. The cavity magnetron, invented at Birmingham University in 1939 and 1940, developed by General Electric Corporation for practical military applications, represented one of the most significant technological breakthroughs of World War II. Its impact extended far beyond immediate military applications. The microwave technology developed for military radar became the foundation for post-war communication systems, television broadcasting, satellite communications, and eventually the microwave ovens found in kitchens worldwide. The industrial expertise developed for magnetron production enabled the electronics revolution of the 1950s and 1960s. The Anglo-American technological cooperation, exemplified by the Tizard mission's sharing of magnetron technology in 1940, established patterns of scientific collaboration that continued through the Cold War and beyond. The decision to deploy revolutionary technology, despite capture risks, influenced military technology policy for decades. The cavity magnetron demonstrated that operational advantage from advanced technology outweighed the risks of enemy exploitation, provided that industrial capacity could produce the technology in quantities the enemy could not match. This principle guided Western military development through the jet age, the nuclear era, and into the information age. The willingness to field new capabilities quickly, accepting that adversaries would eventually copy or counter them, proved more effective than attempting to maintain perfect security while technology remained in laboratories. For the German U-boat force, the story ended in surrender and scuttling. On May 4, 1945, Grand Admiral Dönitz, briefly serving as German head of state after Hitler's suicide on April 30th, ordered all U-boats to cease offensive operations. On May 8th, after Germany's unconditional surrender, Operation Deadlight began. All boats still at sea were ordered to surface, fly black flags, and proceed to designated Allied ports for surrender. Many commanders instead scuttled their boats, unwilling to surrender the vessels in which their comrades had died. Over 200 U-boats were deliberately sunk by their own crews rather than surrendered to Allied forces. The men who had served in those boats, the 75% who died and the 25% who survived, had fought a campaign decided not by courage or tactics, but by physics and engineering. They had been defeated by electromagnetic radiation generated by a block of copper machined in British factories, installed in Allied aircraft and ships, deployed in quantities German industry could never match. The examination of one captured radar set in February 1943 had explained their doom, revealing the electromagnetic dimension of warfare in which Germany had been fighting blind while the Allies possessed clear vision. The story of Type 271 radar is ultimately about the decisive advantage that advanced technology provides when deployed at industrial scale against opponents who lack the scientific knowledge, industrial capacity, and material resources to match or counter it. It demonstrates the psychological impact of fighting enemies who possess capabilities you cannot match, transforming confident warriors into hunted prey through the revelation of technological inferiority. Most fundamentally, it illustrates how innovation in warfare comes not just from laboratories and factories, but from the operators who learn to use new weapons effectively under combat conditions. The radar technicians aboard HMS Hesperus and hundreds of other escort vessels never received recognition for the techniques they developed. Their names do not appear in histories of World War II technology. There are no monuments to the operators who spent thousands of hours staring at cathode ray displays, learning through experience to distinguish meaningful contacts from electronic noise. But their contribution was decisive. They transformed an experimental technology into an operational weapon. They developed the tactics and techniques that made radar effective against submarines. They created the body of knowledge that allowed the technology to scale across the fleet. This was innovation in its truest form, practical problem-solving under pressure, learning by doing rather than by formal study. The clickable title about an unauthorized trick that let destroyers hit U-boats in total darkness contains a fundamental truth, even if the details are more complex than any single anecdote can capture. The real trick was not a single modification or technique. It was the accumulated learning of hundreds of operators who figured out how to make new technology work under conditions its inventors never anticipated. It was commanders like Macintyre who trusted the equipment enough to conduct high-speed attacks in total darkness against targets they could not visually confirm. It was the willingness to learn from mistakes, to adapt tactics to technology, to share knowledge across the fleet so that every ship benefited from every lesson learned. This process was not authorized in any formal sense. There were no official programs to develop radar interpretation techniques. There were no research projects studying optimal methods for tracking submarines through heavy seas. The learning happened organically, driven by operational necessity, refined through trial and error, transmitted from experienced personnel to novices through demonstration rather than documentation. By any reasonable definition, this was unauthorized innovation, not in violation of orders, but simply outside the formal structures of military development. It was sailors solving problems because the problems needed solving, using whatever methods worked, teaching others what they had learned, building a body of practical knowledge that no laboratory could have developed. And it won the Battle of the Atlantic. Consider an alternative history where this learning process did not occur, where Type 271 was deployed to ships but operators never developed the skills to use it effectively, where commanders remained skeptical of technology they did not understand and continued relying on traditional visual and sound detection methods, where the accumulated knowledge of what contacts looked like, how to distinguish U-boats from false returns, when to trust the radar, and when to remain skeptical, was never transmitted across the fleet. In that alternate timeline, the cavity magnetron remains a brilliant invention that fails to achieve operational impact. U-boats continue operating with relative impunity at night. The Battle of the Atlantic drags on through 1944 and possibly into 1945. The invasion of Europe is delayed or impossible due to inability to guarantee supply lines across the Atlantic. Hundreds of thousands of additional soldiers and civilians die in a war prolonged by failure to exploit available technology. This is not speculative fantasy. This is what would have happened without the operational art developed by radar operators and escort commanders. Technology alone does not win wars. Technology effectively employed by trained personnel operating under sound doctrine wins wars. The story of Type 271 demonstrates this principle with unusual clarity. The British had invented the magnetron. The Americans had manufactured it in quantity, but neither invention nor production was sufficient. The decisive factor was the learning process that occurred aboard escort vessels in the North Atlantic, as operators figured out through experience how to make the technology actually work against an intelligent, adaptive enemy. This lesson remains relevant today. Modern military forces spend vast sums developing advanced technology, from stealth aircraft to precision-guided weapons to artificial intelligence systems. But the effectiveness of these technologies depends ultimately on the operators who employ them, the commanders who devise tactics to exploit their capabilities, the organizations that can learn and adapt faster than their opponents. The sailors aboard HMS Hesperus in 1942 and 1943 did not think of themselves as innovators. They were simply doing their jobs, trying to survive in a brutal campaign that killed without mercy or warning. But through their accumulated experience, their willingness to experiment and learn, their unofficial sharing of knowledge across the fleet, they transformed naval warfare as profoundly as any laboratory breakthrough. The night of December 26, 1942, when Hesperus detected U-357 in total darkness and rammed her before she could dive, was not a fluke. It was the culmination of 9 months of learning how to use Type 271 effectively. It was proof that the technology had matured from experimental equipment to reliable weapon. It was validation of the investment in training, in equipment installation, in the patient development of operational doctrine through trial and error, and it was a death sentence for the German U-boat force. Once the technology worked reliably, once operators could consistently detect submarines at night, once commanders trusted the radar enough to conduct attacks based solely on electronic contacts, the darkness no longer protected German submarines. The fundamental advantage that had allowed U-boats to dominate Atlantic shipping for 2 years evaporated. Dunitz's mathematical calculations about sinking rates and replacement rates became irrelevant because his boats could no longer operate effectively. The strategic outcome was determined not by a single battle or even a series of battles, but by the cumulative effect of a technology deployed at scale and used effectively. Every U-boat forced to remain submerged to avoid radar detection was a U-boat moving slowly, consuming battery power, unable to intercept convoys. Every U-boat sunk by radar-directed attack was a crew of trained sailors who could not be replaced, a boat that cost enormous resources to build destroyed before it could achieve significant results. Every merchant ship that reached port safely was tonnage that remained in service, cargo that reached its destination, supply lines that stayed open. The mathematics were inexorable once Allied radar achieved operational effectiveness. Germany was losing the war of production. American shipyards were building merchant vessels faster than U-boats could sink them. Liberty ships that had required over 200 days to construct in 1941 were being built in 42 days by 1944. At peak production, American yards were launching approximately 3 Liberty ships every 2 days. German U-boats sinking an average of 3,000 to 5,000 tons per boat before being destroyed simply could not match this production rate. As long as Allied shipyards could replace losses faster than U-boats could inflict them, the campaign represented strategic defeat disguised as tactical success. The only way to win the tonnage war was to maintain an unsustainable exchange ratio, while simultaneously avoiding losses that Germany could not replace. Allied radar made both objectives impossible. The numbers defining the impact remained staggering. Type 271 and its successor systems equipped hundreds of escort vessels during the war. These ships participated in thousands of convoy battles, directly contributing to hundreds of U-boat kills. But the indirect effect was even more significant. Thousands of U-boats were forced to operate submerged to avoid radar detection, reducing their effectiveness even when they were not directly attacked. Thousands of convoy passages occurred without incident because U-boats could not approach undetected. Thousands of merchant ships reached port safely, delivering millions of tons of war materials that sustained British resistance and enabled the invasion of Europe. The cavity magnetron, transformed from laboratory curiosity to war-winning weapon through the efforts of operators who learned to use it effectively, shortened World War II and saved countless lives. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.